Hey guys, Professor Dave here. I want to talk to you about stereoisomers, especially enantiomers and diastereomers.
He knows a lot about the science stuff. Professor Dave explains.
So, we're probably familiar with the term isomerism and understand a little bit about what isomers are, but there's different kinds. And we may recall what structural isomers are. Structural isomers are molecules that contain the same molecular formula, but differ in connectivity. In other words, the same number of the same types of atoms, but connected differently. So here's an example of two different butanes. We have straight-chain butane and isobutane. They're both C4H10, but they're connected differently, right? As opposed to the straight chain, one of these carbons has been moved over to the middle. So those are structural isomers. Now, stereoisomers are compounds that have the same molecular formula and the same connectivity. In other words, the same atoms connected in the same way. However, they differ in the way they are oriented in three-dimensional space. So something like this, we can see that it is the same atoms bound in the same manner. However, they differ in the way that they are oriented in three-dimensional space. And let's talk a little bit about why. So the first kind of stereoisomeric relationship I want to talk about involves molecules that are called enantiomers of one another. Enantiomers are molecules that are non-superposable mirror images of each other. In other words, they are stereoisomers, so they have the same connectivity, but if you take the mirror image of one of the compounds, you get the other, and they're not the same because they do not overlap precisely the same way in three-dimensional space. So take, for an analogy, our hands. So here's one of my hands, and the mirror image of this hand is my other hand, right? So these have an enantiomeric relationship in the sense that they are mirror images of one another, but they do not precisely overlap. I'm not going to be able to get every finger to overlap its corresponding finger properly. So they have an enantiomeric relationship because they are non-superposable mirror images of one another. And we can come up with all kinds of macroscopic examples of this. But molecules are doing the same thing. So let's take something like this molecule and let's reflect it across a mirror plane here. And we can all agree that this is the mirror image of that. Right, so we have X, whatever these atoms are, it doesn't matter. X, and then the Y, and then the Z, these are mirror images of one another. But now, if we rotate the resulting mirror image to try to place it on top of the original, so in order to do that, if we want the X to line up, we're just going to twist this like a top 180 degrees, and we would get this. But the problem is, if we try to take this and put it on top of that, not all of the atoms are going to overlap properly. So the W, the central atom, and the X, those would overlap just fine, but you'd find that the Y would be on top of the Z, and the Z would be on top of the Y. Therefore, this molecule and its mirror image, which are two distinctly different molecules, are enantiomers of one another because they are non-superposable mirror images of one another. So molecules that have an enantiomer display a quality called chirality. This is something that we would typically assign to a carbon that has 4 different substituents projecting from it. So for example, on the top, this carbon atom has a bromine atom, the implied hydrogen, and 2 identical methyl groups. So we would not regard this as chiral because it has 2 identical methyl groups, so it does not have 4 distinctly different substituents. Now, this would mean that this does not have an enantiomer because if you made the mirror image of this molecule, it would be precisely the same molecule. It would be superposable, so it would not have an enantiomer. Its mirror image would be identical, and it is therefore not chiral. However, this molecule is chiral because this carbon has a bromine atom, the implied hydrogen, this 1 carbon chain, and then a 2 carbon chain. So that is 4 distinctly different groups, and if we went and took the mirror image, we would see that it is that. And now, if we try to flip that around we would get the same structure, but now the bromine would be on the dash bond, because if the bromine atom is on the wedge bond out of the board like this, if we flip the whole thing 180, now the bromine is going to be going into the board. So if we try to place this on top of that molecule, it is not going to line up properly. So therefore, this molecule is chiral. It has a chiral center, or a center of chirality, or a stereogenic center, all terms that mean the same thing, and therefore it does have an enantiomer. Likewise over here, this is a carbon with 4 different groups. This is a similar molecule, but 2 of the groups are the same. We have 2 fluorine atoms. So if you at home want to go ahead and check, you could draw the mirror images of both of these compounds, and you could see that this is chiral because there is no way to rotate its mirror image so as to place it upon the original and have it line up flawlessly. However, this one over here, having 2 identical fluorine atoms, if you drew the mirror image of this molecule, there is a way that you could rotate it so as to make it flawlessly superposable. Therefore, this cannot be chiral. This is achiral. A meaning a prefix that implies not. So this is not chiral. It does not have a mirror image that is distinctly different from the original. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me with questions, ProfessorDaveExplains@gmail.com.